think we're going. Ziyan is a Maury visiting assistant professor in the Department of Mathematics of the University of California, Berkeley, hosted by Professor Lindbladian. Previous to that, he received his PhD degree in mathematics from the University of Wisconsin-Madison under the supervision of Chin Lee. His research interests lie on numerical analysis, machine learning, and quantum computing, in particular the theoretical analysis and numerical simulation of high-dimensional problems. Let us all welcome our speaker.
Okay, yeah, so thank you for the brilliant introduction. My name is Ziyan Ding, and it's my great pleasure to introduce our recent work in this online seminar. So today in this talk, I will talk about the single ancilla ground state preparation via Lindbladians, and this is our recent work with Anthony Chen, who is a PhD in Caltech, and my postdoc mentor, Professor Lindbladian. Okay, so essentially, in this paper, our goal is to solve the following problem. So given a Hamiltonian capital H, how to prepare the ground state of capital H with a zero initial overlap. So essentially, we want to solve the ground state preparation problem. So basically, given a Hamiltonian H, we want to prepare its smallest eigenvector, and we call it the ground state. And in our talk, we will denote this ground state as psi zero. So the first thing I want to say is this problem is a QMA hard in the worst case, meaning that it's super hard for us to find an efficient algorithm to prepare this psi zero only using the information of capital H. And our algorithm and our goal is not breaking this QMA hard bottleneck. So basically, our algorithm will still meet fit into this QMA hard regime. Okay. So then for the ground state preparation problems, so when people want to develop an algorithm, and a common additional assumptions to overcome this QMA hardness is they assume that we already have a good initial state phi. So basically, we can have a quantum state to construct a good initial state. And in this setting, we say that this initial state phi is very good, meaning that if you calculate the overlap between this initial state and the ground state, we denote it as a P0, then this overlap will at least be 1 over poly n, where n is the number of qubits. So basically, if you look at all the previous QPE methods or many post-QPE methods to construct construct a ground state with overlap larger than 0.5, larger than 0.9 or even 0.99, they always need to assume that we already have a good initial state whose initial overlap is at least 1 over poly n. Okay, so the key reason this QPE and post-QPE methods need this good initial overlap is basically in these algorithms, they are doing something like filtering process. Essentially, what you do is you first draw the energy landscape of your initial state, where this x-axis is all your eigenvalues, and the y-axis is the overlap between your initial state and the ith eigenvector. So basically, you can see this lambda 0 and the p0 here. So now, because we only care about the ground state, then basically what we can do is we can try to construct a filter function on this energy landscape, and the goal of this filter function is let us get rid of all the high energy eigenvectors. So basically, after filtering, you can see that we can almost only see the ground state. Then essentially, you only need to observe the energy, then you can directly get the ground state. However, one big problem of this filtering idea is it does not work if my P0 is very small. So here means that so if my P0 is exponentially small in the number of qubits, then this filtering method will be very expensive. Why? The reason is on the quantum computer, all the quantum operations is CPTP. This essentially meaning that so even if we can do the filtering process to filter out all the high energy eigenvectors, however, even after the filtering, the probability that we observe this ground state is still P0. So essentially, with the probability 1 minus P0, we will observe some trash, and we know they are trash. Okay, but to find the ground state, since our success probability is P0, the number of repetitions will be P0 inverse. So if my P0 is exponentially small, then I need exponentially many number of repetitions of my algorithm. So the complexity will be exponentially in N. So yeah, so it's not very good. Okay, so then now one question is it possible to find some ground state preparation algorithms so that we can eliminate this initial overlap dependence? So so essentially, we want to find some algorithm that can work for bad initial state. And in general, this problem is QMA hard. So basically, this means that we cannot prepare the ground state efficiently just by knowing capital H. Okay, and according to the QPE or the post-QPE method to do the ground state preparation, we know that the initial overlap of P0 equal to 1 over poly n is some sufficient condition. However, whether it is a necessary condition, so we don't think so. We think that we can borrow in other assumptions to replace the assumptions on P0. And there are actually several examples. So for example, to do the ground state preparation, we can also design some parameterized circuit. So such as VQE, MPS, or DMRG. So basically, on the very high level, all of these methods are trying to construct some variational quantum state to approximate our ground state. And by optimize the parameter in this variational quantum state, we can make sure that the overlap between the variational quantum state and the ground state is large. Okay. However, one big problem of this parameterized circuit is it's very hard to analyze the complexities of the optimization process, and also it's so we don't know how this is how the optimization process scales with the size of your system. And another another idea is try to use the adiabatic theory. So basically, now if I want to construct the ground state of capital H, one idea is we first find a good so we first find another good Hamiltonian H0 such that we have access to the ground state of H0. Then we try to build some dynamics to construct and to connect this H0 with H. And by simulating this dynamics, the ground state of H0 will automatically changes to the ground state of capital H. Okay. However, the problem with the adiabatic theory is how to find a good H0 to prepare the ground state of capital H. And in general, this is a very hard the problem. And for large system, how to find this H0 is very unclear. Okay. So in our paper, we try to introduce a new idea for the ground state preparation, which is using the Lindblad dynamics to do the ground state preparation. Actually, this idea is inspired by many recent works for the thermal state preparation. So essentially here you can see a lot of recent works, and so where in these papers the author try to develop some open quantum system to prepare the thermal states. Okay, and in all of these the papers, instead of assume that we have a good initial state, the key theoretical assumption is about the mixing time. So we assume that the dynamics we build has a poly-n mixing time, then we can do the efficient construction. Okay. So now, so this PPT is kind of the most important PPT in my talk. It essentially tells you why the Lindblad idea might work for the ground state preparation. So here, by using Lindblad dynamics to do the ground state preparation, what we are essentially doing is not a filtering process. We're actually doing a shuffling process. So basically, in the previous QP or post QP method to get the ground state, what we do is we build a filter function to filter out all the high energy eigenvectors. However, because the quantum operation is a CPTP, this might not be very efficient. Then in the Lindblad dynamics, instead of doing this filtering process, we actually want to shuffle the high energy eigenvectors to the low energy eigenvectors. Essentially, so here we want to shuffle the first excited state to the ground state and the high energy state to the ground state. And since the whole process is still CPTP, we can make sure that after the shuffling, the initial overlap will be approximate to 1. And the advantage of this is if we can show that the mixing time of the Lindblad dynamics is a poly-n, then the whole algorithm will always succeed with a probability closer to 1. And this whole process is independent of a p-naught, meaning that the algorithm can work for every initial state. Okay, and we only need to give some assumptions for the mixing time. Okay, because this is the most important PPT. And any question here? Okay, so if there's no question, then I can move on. So now I will introduce our algorithm. So basically, our algorithms is based on the Lindblad dynamics for open quantum system, and this equation is essentially it's called the Lindblad master equation. So here, this first term we call it the coherent part on the quantum computer. It's equivalent to the Hamiltonian simulation. And for this part, we call it the jump operator, where this K is some matrix. Okay, so the Lindblad dynamics is actually a tool for us to understand the open quantum system. So basically, if we have a open quantum system part here, now we have the system Hamiltonian. We also have an environment Hamiltonian, and if you consider the interaction between the system and the environment, we will also have a total system Hamiltonian. Then so now what we can do is we can evolve the total system using this H capital T, and then at each time t we can use the trace out process to trace out the invariant part, and we only care about how the density operator in the system part changes. And after do some calculations and some approximations, we can show that we can always use this Lindblad master equation to describe the evolutions of my system, meaning that my rho can satisfy the following equation. Okay. Now we will try to design a specific Lindblad dynamics for the ground state preparation. And so here I first want So any question?
What's the script H and capital H? What's the difference?
You mean yeah. So so I think this capital H is the Hamiltonian part, but this curly H actually I forget what's its meaning. It might mean the Hamiltonian simulation part. Yeah. So because this is just a picture borrowed from the previous papers. Yeah. Okay, sorry. Yeah.
Hamiltonian or one is. Okay. Thank you.
Yeah. Okay. Yeah. So other questions? Okay. Yeah. So now I want to give a quick introduction for the solution map of the Lindblad dynamics. So essentially, when we write down this Lindblad dynamics for any given t, we can define the following solution map tt, where it maps the initial density operators to the density operators at time t. Okay, so here, if we want to simulate this Lindblad dynamics, one disadvantage of this solution map is it's not a unitary map. So this essentially means that to simulate this Lindblad dynamics, we cannot directly use the Hamiltonian simulation, because it's not a unitary map. We need to do some other things, and I will show you later. But the advantage of this solution map is this map TT is always a CPTP map, meaning that it is completely positive trace preserving. Okay, this essentially means that there is so basically this means so after doing this solution map, my rho t will still be a density operator. And if we can efficiently simulate this Lindblad dynamics on our quantum computer, then there is a hope to get success probability 1. Yeah, because it's a trace preserving map. So it can always so if we do our algorithm good enough, it can also guarantee very high success probability, and you will also see this later. Okay, so now before introducing our construction, I first want to give you simple examples for you using the Lindblad dynamics to construct the ground state. So now we consider a 1-qubit system where my capital H is a -c. Okay, and I only have one jump operator where this capital K has the following form, and we assume that at time t equals to 0, my initial state is the first excited state. So my initial density operator rho 0 has the following formula. Then you can kind of imagine this is almost the worst case, because at the time t equals to 0, the initial overlap between my initial state and the ground state is actually equals to 0. Okay. However, if we plug everything into my Lindblad dynamics and we try to calculate the solution map, we will see that the solution map has the following formula. So basically, after you do the calculation, you will see that when my t approaches to infinity, this rho t will converge exponentially fast to the ground state. Okay, so by doing this calculation, we see that even my initial state has overlap 0. We can still using this Lindblad dynamics to approximate the ground state very fast. Okay, and here now let's see why this idea can actually works, or why so so why this dynamics can help us prepare the ground state? There are actually two key reasons. If you focus on so now for simplicity, we can first ignore the coherent part, and we only focus on the jump operator part. Okay, so basically now, if you look at the jump operator part, and you plug in the first excited state, by doing some calculation, you can actually show that the jump operator part will map the first excited state to the ground state. So on the high level, it means that the jump operator part can help you to push the high energy state to the low energy state. And it can always help you decrease the energy of your system. And furthermore, if you are already at the ground state, then if you plug in the jump operator part, it will give you 0. Okay, so essentially this means that it can help you preserve the ground state energy. Okay, so now if you plug this part into your equation, and also since the coherent part can always keep the eigenvector, you will see that if my rho t already equals to the ground state, then this is then this d rho dt will always equals to 0. This essentially means that the ground state is equilibrium of this Lindblad dynamics, and we can hope that when we run this Lindblad dynamics for enough long time, my density operator rho t will converge to the ground state. And here, by doing this calculation, you will see that these two equations are very important for our Lindblad dynamics for the ground state preparation. Okay. Yeah. Okay. Okay. So here in the previous Lindblad dynamics, we actually can call it as the ergodic Lindblad dynamics. So what ergodic is actually borrowed from the classical Markov chain. So essentially, given our Lindblad dynamics, we say that this dynamics is ergodic, meaning that this dynamics has a unique fixed point rho infinity, such that for any initial state, if I push t to infinity, my rho t will converge to the rho infinity. And also, this ergodic Lindblad dynamics has a mixing time, meaning that starting from any initial condition, if we run this Lindblad dynamics for time capital T, then the distance between my density operator rho t and its fixed point rho infinity can shrink by 1/2. So now, if we have this mixing time, so it's actually very important for our complexity analysis. So basically now, if we have a finite mixing time, then we can show that given any epsilon larger than 0, to find a good approximations to my rho infinity, I only need to simulate the Lindblad dynamics with time t in the following form. So this time t will be linearly dependent on my mixing time and only log depend on 1/epsilon. And more importantly, this time t is actually independent of rho 0, meaning that it can work for arbitrary initial state, and we don't need any assumptions for the initial overlap. And that's why this mixing time is very important in our Lindblad dynamics. Okay. Okay. So actually, in the past few years, people have developed some Lindblad dynamics for the thermal state preparation. So essentially, in this works, people try to use Lindblad dynamics as an algorithm tool to prepare the ground state. So essentially, you write down some Lindblad dynamics, and try to construct some jump operators. Then by simulating this Lindblad dynamics, we can show that it can drive the system to the thermal state, meaning that when t goes to infinity, my rho t can convert to some rho beta, where beta is a fixed number. So, this is the formula of the thermal state. So essentially, in these papers, to construct a Lindblad dynamics for the thermal state preparation, you need to construct the dynamics so that it satisfies some quantum detailed balance condition, meaning that it can always fix the thermal state. So essentially, if I plug the thermal state into the right-hand side of this equation, it can equal to 0, meaning that the thermal state will be an equilibrium for this Lindblad dynamics. Okay, so now what we want to do is we want to extend this idea to the ground state preparation, and actually, so if you can accept that the Lindblad dynamics is a good algorithm tool for the thermal state preparation, you can always do a very naive extension. Essentially, what we can do is we run this equation 1 with some beta very closer to infinity. Then what we can show is when we let t go to infinity, my rho t will converge to rho beta, and since my beta is very large, meaning that the temperature is very low, then in this case, my thermal state will be very close to the ground state. So this rho beta will be very close to my ground state, and essentially, we are approximately doing ground state preparation. However, the disadvantage of by doing this is when we prepare the thermal state, we always need very complicated and many jump operators, and we also need to do an approximation here. How this approximation will affect our complexity is still unknown, and also we need many jump operators, which is kind of very expensive. So the reason when we do the thermal state preparation, we need a lot of jump operators is because the detailed balancing condition for the thermal state is complicated. To make sure that the Lindblad dynamics satisfies this detailed balancing condition, it's not very easy. Okay. However, for the ground state preparation, its detailed balancing condition is much simpler. And what we can do is we can use the Lindblad dynamics to prepare the ground state using only one jump operator. So basically here, in our Lindblad dynamics, we only involve one jump operator k, where k has the following formula. So yeah, so this formula seems a little too complicated, but essentially, for a fixed s, what you do is you first do a forward Hamiltonian simulation, then you apply some coupling matrix capital A, then you do a backward Hamiltonian simulation. Essentially, to simulate this operator k, you need to do the linear combinations with different s. Okay, so here why we use this formula, it's essentially because that if you rewrite this integral form into its Fourier transform, so basically what you can do is you can try to you can try to rewrite the matrix A in the eigenbasis of capital H. Here, this psi I and psi j is the eigenvectors of capital H. Then after doing this integral, you can rewrite this fs using the Fourier transform of my f, where this lambda I and lambda j is the eigenvalues of my capital H. Okay, so now you can look at this term. So for simplicity, you can first ignore this A part. Okay, so let us first ignore this A part, and if you only look at this term, what this term is does is you give me this eigenvectors of capital H. So basically, you give me psi j, then this term will change this psi j to psi I. Okay. So now, since we are doing the ground state preparation, what we hope is we can always push the high energy state to the low energy state. This essentially meaning that if the energy of my psi I is larger than the energy of my psi j, then we don't want to make the change. If the energy of psi I is smaller than the energy of psi j, then we want to make the change. And since this lambda I and lambda j is the energies, this essentially meaning that if this lambda I is larger than lambda j, I don't want to make the change. And if lambda I is smaller than lambda j, then I want to make the change. And since since in our algorithm development, we can choose this fs by ourselves, then this means that we can have full control of the head of f. And essentially, I only need to design some function f such that the f hat omega equals to 0. If my omega is a non-negative number, then I plug it in. I can rewrite this this summation part into the following formula. So basically here, the only remaining term is where this lambda I is smaller than lambda j. Essentially, this means that by applying this jump operator k to psi I, it will output some psi j such that the energy of this psi so it will output some psi I such that the energy of psi I is always smaller than the energy of psi j. So essentially, it will keep pushing the high energy state to the low energy state. And the advantage of this development is it's actually very flexible with the coupling matrix A. So basically, in our algorithm, you only need to choose this A to be a Hermitian matrix and not block diagonal in the eigenbasis of capital H, then it can always work. And you can even choose A to be a local operator to help your simulation. Okay, so basically, it's very flexible to choose the coupling matrix A. As long as you choose your F to satisfy this condition, the jump operator K can always fix the ground state. Okay, so basically now if I design my matrix K using the following form, we can show that the corresponding jump operator LK can always fix the ground state, which is very good. And also, it can always push the high energy state to the low energy state, meaning that the overlap between the outcome of this jump operator and the low energy state is always larger than 0. And more importantly, the low energy state cannot go to high energy state, meaning that the overlap between between this outcome and the overlap between high energy state always equals to 0. So essentially, using this jump operator, we can keep pushing the energy down. Okay. Okay. So in our algorithm, yeah.
So A, F, and A are chosen. So
yeah.
They both depend on the Lindblad. I mean, it's easier to understand A is some coupling matrix you want to choose to satisfy the requirement. How do you prepare F? I mean, are they like some arbitrary function, or they must be depending on the Lindblad?
So this is a very good question. In our algorithm, we need to choose A and F. But the choice of A is very flexible. You can choose you only need to choose it to be a Hermitian matrix. It can even be local, and to choose this function f, it only needs to satisfy this assumption. But to simplify our simulation, we also hope it can satisfy other assumptions. And actually, in my next PPT, I will give an examples of f. Yes, so essentially in our paper we chose say chose this f and there are some parameters and I will explain why we make this choice.
Okay.
Okay. Yeah. Okay. So basically, in our paper, we will try to choose the function f into this form. So this looks like a very complicated formula, but essentially, we only want to choose this f to satisfy the following condition. So basically, so here I try to draw draw the graph of f hat and fs. So if you look at the graph of f hat, you can see that it's almost like an indicator function. So essentially my f hat will be will equals to 1 once this omega is very close to 0 and equals to 0. If this omega is larger than 0, and furthermore, my fs will decrease to 0 very fast. So here in our choice, there are some parameters. Here I will choose my a and delta a almost equals to the norm of h. So the reason for this choice is we want to ensure the cross jump in our Lindblad dynamics, meaning that if I'm at the second excited state, there is some hope to directly jump to the first to directly jump to the ground state. And here we choose my b and the delta b, so closer to the spectral gap between lambda and lambda 0. This can actually help us to ensure that if I'm at the first excited state, it can jump to the ground state. Okay, and also so in our construction of fs, you will see that the magnitude of my fs will exponentially decay to 0. It can actually help us so help our simulation. We recall that in our previous jump operator, our k has the following integral formula from -infinity to infinity. Then in our simulation, we must truncate this integral. Then if my fs decays very fast to 0, 1s go to infinity, then it's very easy for us to do the truncation. Okay. Yeah, but I want to emphasize this is only one possible choice of f. So actually the choice of f is very flexible. You only need to make sure that it satisfies this condition, and we do expect that so there exists a better choice of f to accelerate the whole process. Okay, so now essentially this is our Lindblad dynamics for the ground state preparation. So basically, in this dynamics, we have the coherent part, and we also have the jump operator part. The important part is we only have one jump operator k, which can be written into this formula. And this Lindblad dynamics has two good properties. First, it can always fix the ground state, meaning that the ground state is the equilibrium of this Lindblad dynamics. And the second, this Lindblad dynamics can push the high energy state towards the low energy state. Essentially, by running this Lindblad dynamics, the energy of my system can keep decreasing until it reaches to the ground state. Okay. Yeah. So essentially, this is our Lindblad dynamics. Okay. So now our main result is as follows. So basically, given a Hamiltonian capital H, we want to prepare its ground state, and we assume that the spectral gap between lambda1 and lambda0 is larger than delta, and we assume that we have queries to the Hamiltonian simulation, and we measure the cost of our algorithms by the total Hamiltonian simulation time. And we hope that the total Hamiltonian simulation time of our algorithm is not very large. And we measure the error by the trace norm of rho with respect to the Lindblad dynamics. So essentially in our paper, we introduce an algorithm to simulate the Lindblad dynamics with high accuracy. And if the Lindblad dynamics can converge, then our algorithm can also succeed. Okay. So basically, there are several features for our algorithm. So first, the most important feature is our algorithm has the ability to prepare the ground state from zero overlap. Essentially, even you give me an initial state with zero overlap with the ground state, it can still succeed. And we only require one jump operator for our Lindblad dynamics. And later, I will show you a simulation method that only requires one ancilla qubits. Okay. And for the simulation cost, if we want to accurately simulate the Lindblad dynamics, then if we stop our algorithm at some time t mixing, then the total Hamiltonian simulation time will quadratically depend on t mixing and linearly depend on 1 over epsilon. So essentially, it's our first order method. And also, it will linearly depend on the norm of h and linearly depend on 1 over delta, which is a special gap. So the reason we will have this 1 over delta is because previously in my function f, I choose my b and the delta b to be order delta. Okay. So here, if you look at the complexity of the continuous time simulation, one disadvantage is we only have first order methods, which makes the complexity quadratically depend on the t mix and linearly depend on 1 over epsilon. But actually, we can also do some some very surprising thing called the discrete time simulation. So this name is a little weird, but essentially this means that we want to simulate our Lindblad with a very large step size. So I will explain this discrete time simulation in detail later. Essentially, we want to simulate a discrete version of the Lindblad dynamics. And if we do the discrete time simulation, then we can get some quadratic improvement in capital T. So the complexity will only linearly depend on T mix, and we can also get arbitrary polynomial improvement in epsilon. So the total complexity will only the polylog depend on epsilon, and furthermore, we can get exponential improvements in the norm of capital H. So essentially, if you look at this complexity, the norm of H will appear in the log part. Okay, so basically, so overall, we can get the quadratic improvement in the gate to cost, which mainly come from this capital T part. Okay, so now here I want to emphasize that the result in the third and the fourth point is only the simulation cost. Here, when we discuss the complexities of our algorithm, you will see that we require some information for the Tmax. However, a rigorous discussion for the Tmax is a very hard problem in general. Yeah. So so currently we are trying to do something to find an upper bound for this T mix. However, in general, it's a very hard problem, and we can only do this for like some very simple Hamiltonians. Okay, and in our paper we have another class discussing for the mixing time, and these are kind of initial results for the discussions for the mixing time. Essentially, if we assume that we have some random coupling matrix A, meaning that my matrix A is a random matrix. This assumption is mainly motivated by the eigenstate thermalization hypothesis called ETH hypothesis in physics. Then if I have a random coupling matrix, I can show that the ground state is a unique fixed point of my Lindblad dynamics. This essentially means that my Lindblad dynamics will always converge to this ground state. And furthermore, if we assume some additional structures on the entries of A, then my Lindblad dynamics can converge to the ground state in poly-n mixing time, meaning that the T mix in my previous result will only be poly-n. So then we can finally find a poly-n and complexity algorithm for the ground state preparation. Okay. However, the key problems of this result is it needs to assume some random coupling matrix, which is not true in real applications, and how to impose these additional structures in our real algorithm is also unknown. So then two very important open problem is so can we guarantee that this ground state is a unique fixed point without strong assumptions? And can we show the polynomial mixing time without strong assumptions? And to my best knowledge, I think these two problems are still open, and we believe they are very hard problems. Okay, yeah. Okay, so this is some numerical results for our Lindblad simulation. In our paper, we actually tested the TFRM4 model, TFRM6, and the Hubbard 4 model. And for all of these models, my Lindblad dynamics can converge to the ground state. So here, if you look at the left part of the graph, you can see that by simulating the Lindblad dynamics, my energy can keep increasing, and in the middle graph and the right graph, the overlap between the initial state can increase to 0. Okay, and here in these two lines, in this red line, we are doing the discrete version of the Lindblad simulation, and this blue line, we are doing the continuous time Lindblad simulation. You can essentially see that for these two different versions, they will all converge to the ground state. Okay, with a similar Lindblad simulation time, but in the discrete version of the simulation, the total Hamiltonian simulation time is 1 order cheaper, meaning that we by using the discrete version of simulation, we can reduce the computational cost. Okay. Okay. So now in the last part of my talk, I want to give I want to quickly go through our quantum simulation algorithm for the Lindblad dynamics. So in fact, in the literature, we already have a lot of algorithms for simulating the Lindblad dynamics, and you can see that in these recent works, we can almost achieve the optimal cost, meaning that the total cost for simulating the Lindblad dynamics will be linearly dependent on capital T, and only polylog dependent on T over epsilon. Okay. However, here, if we directly want to implement this quantum algorithm for simulating our Lindblad dynamics, one key difficulty is our jump operator K has the following complicated formula. So in all of the previous algorithms, they always need to assume that we have a block encoding for the jump operator K to run the algorithm. But since our jump operator K has the following complicated formula, assuming we have a block encoding for K is not very reasonable, we need to do some different thing, okay? And also, the idea of the discrete time version of the Lindblad dynamics is, so you will also see it later. So essentially, we only need the fixed point argument. We actually don't need the Lindblad dynamics, okay? So now I want to give a quick review for the simulation part. So essentially, the first step of our simulation is we try to use the first order charter to separate the coherent part and the jump operator part of my Lindblad dynamics. So essentially, so I use the first order charter splitting here, and the first term is essentially the Hamiltonian simulation, and the arrow is order tau square. Okay, so here this blue part is the simulations for the jump operator. Actually, it's not very easy. The reason is also it's a CPTP map. It's actually not a unitary operator, so it's not a Hamiltonian simulation. We need to simulate it using a different way. And the key idea is borrowed from a previous paper by Cliff and Wang in 2016. Essentially, given a matrix K, we can try to introduce a dilation matrix K tilde such that we put the such that we put the matrix K in the left bottom corner, and we put the K dagger in the right upper corner. Then this K tilde will always be a Hermitian matrix. Then, since this K tilde is a Hermitian matrix, we can do the Hamiltonian simulation for this Hermitian matrix K tilde on the quantum computer. We only need to add one ancilla qubit here. Then we do the Hamiltonian simulation part. Then after doing this Hamiltonian simulation, we do some trace out process, meaning that we will measure the ancilla qubits, but we don't care the output of the measurement. We just measure the ancilla qubits and we discard the ancilla qubits. Then we can show that actually by doing this Hamiltonian simulation and the trace out process, we can get a first order approximation to the jump operator simulation part, meaning that we can approximate this exponential LK tau up to order tau square. And the important part for this trace out process is, since we don't care about the output of our measurement, this whole process will always succeed with probability 1. So what you need to do is you do some Hamiltonian simulation, do some measurement, discuss the outcome of the measurement, then reduce the whole process again and again. Okay, then essentially now by doing these two steps, our simulation algorithm can be simplified to how to simulate this K tilde. Okay, then so this is a quick idea for the simulations of K tilde. If I recall the matrix K, so it has the integral form, then we can use the quadrature formula to discretize this integral form and written it into a summation form. And for each of these small terms, I name it as Ki. Then basically I can rewrite, so I can further use the second order charter to separate these large Hamiltonian simulations into small Hamiltonian simulations. Here, one interesting thing is, since this simulation time is the square root of tau, Then if we directly use the second order charter, the simulation error will be tau to the 3/2. However, if you do some calculation, you can show that after the tracing out process, the first order error term will disappear. This makes that even so. Also, we only use the second order charter formula for this simulation part. Our final error will still be order tau square, meaning that we can get a first order algorithm. So then, after doing all of this separations, the remaining step is how to simulate this k tilde L. Actually, we can do it very efficiently. So yeah, so basically here I need to introduce the matrix AS into the following form, and we need to do some calculation here. But the basic summary is to simulate. To simulate this KL part, essentially what you need to do is you first need to do a long Hamiltonian simulation, then you need to do a Hamiltonian simulation for a local operator. So yeah, so if you choose this A to be a local operator, then this part will just be a local operator. Then you do a backward of the Hamiltonian simulation. So basically, to simulate this part, we can complete it by the the original Hamiltonian simulation and the simulation for the controlled local operator A tilde. And furthermore, if you combine different long Hamiltonian simulation together, you will also see some cancellation here, meaning that in our simulation algorithm, we can actually avoid long Hamiltonian simulation. Yeah, but this part, you need to do some complicated calculation. Essentially, the key point is you only need to do the Hamiltonian simulation, so you only need to do the short-term Hamiltonian simulation and the Hamiltonian simulation for the local operator A. Okay. Okay. And this essentially can give us the algorithms for the continuous Lindblad simulation. Essentially, the circuit will be something like this. You do some local Hamiltonian simulation part here, then you do a short-term Hamiltonian simulation, and you repeat it again and again to simulate this W square root of tau. Then this is one step of our simulation. After doing this one step, we measure the ancilla qubit, discard the outcome, and repeat the whole process. The important observation is that this is a one ancilla qubit and only required for the simple case. So by doing this continuous Hamiltonian simulation, we have the first order accuracy, means that the final complexity will quadratically depend on capital T and linearly depend on 1/epsilon. Okay. So and actually we can further improve our algorithms using the discrete Lindblad simulation. So the idea is actually pretty simple. Essentially, in our previous algorithm, why we have the first order error is essentially because in the very beginning we use the first order charter to split the concurrent part and the jump operator part, and this step will already use the first order accuracy. However, if you directly look at this formula, you will see that even for very large tau, this formula can still fix the ground state. Then essentially, in our algorithm, what we can do is we only simulate this part with tau equals to order 1. Then we can repeat it again and again. So although now, since I make tau to be order 1, we are not exactly simulating the continuous Lindblad dynamics, will actually simulate discrete versions of this Lindblad dynamics. It can still fix the ground state. We can still converge to the ground state. And if we simulate this discrete Lindblad dynamics, then we can get almost optimal complexity, which is linearly dependent on capital T, and only polylog depend on 1 over epsilon. And this is a discrete time Lindblad simulation. Okay, so finally, some conclusion of my talk. So here in this talk, I try to introduce our open quantum system, actually our Lindblad dynamics for the quantum state preparation, and by some numerical and theoretical result, we can see that the Lindblad dynamics might be a potential candidate for the quantum state preparation, and our algorithm is actually can fit in the region of the early fault tolerant quantum algorithm because it only requires 1 ancilla qubit and a very simple gate. And by using this Lindblad dynamics to prepare the ground state, we can replace the assumptions on the initial conditions by the mixing time. We only need to show that our Lindblad dynamics can mix fast. Then we can get our efficient algorithms. Okay, and there are actually a lot of open problems in this direction. Here in our dynamics, we only need 1 jump operators, but actually. It might happen that if you add more jump operators, the dynamics can mix fast. Okay, and also currently we are not sure whether the coherent part can help us a lot in the Lindblad dynamics. So actually, it does not affect the fixed point argument, but in our simulation, we always need this coherent part to see the faster convergence, and we want to know why. Or so furthermore, you might also develop some non-Markovian dynamics for the quantum state preparation, or even make it variational. Okay, so I have finished my talk, and thank you for the attention and the invitation. Yeah. Okay. Thank you.
Well, thank you very much for your talk. And now we open for some questions if the audience has any more.
Let me share.
Thank you for the nice talk. From my understanding, I think because you claim that the Lindblad has the fixed point, and you try to reduce the mixing time. Is that correct?
Yeah.
And so my question is that if you have Hamiltonian and your Lindblad is fixed, and your fixed point will be fixed, so you have no chance to change the fixed point. So how come the fixed point will be always be the ground state instead of the thermal state? In my intuitive guessing, I will guess the fixed point will be the thermal state instead of the ground state. So how can you frame that?
Yeah. So the key point is so when we design our Lindblad dynamics, we choose us. So we design a specific jump operator K, and here if you look at the formula of our jump operator K, it actually contains the information of the Hamiltonian. So in fact, this jump operator will depend on the Hamiltonian, and we can specifically design this Fs such that this jump operator can always fix the ground state. So the first thing is we can always guarantee that the ground state is at least 1 fixed point for our Lindblad dynamics. And actually, I think you are right. It's possible that the Lindblad dynamics might have a thermal state as another fixed point. Okay, so then currently for general Hamiltonian H, we don't know how to guarantee that the ground state is a unique fixed point. But in our paper, we do show that if my coupling matrix A has a certain good properties, we can guarantee that the ground state is a unique fixed point. Yeah, but it's kind of a weaker result. Okay.
So it's by design of F such that your fixed point will be the ground state. It's by
yeah.
design. I see.
Yeah. So basically, my F hat satisfies this condition. Then I can always make sure that so the ground state will be the one fixed point of my Lindblad dynamics.
I see. So the operator coupling matrix A is not that important. You just choose some random one, and you design F more carefully.
Yeah. Right. So basically, in our algorithm, the matrix A so is not very important. So in fact, if possible, we hope that this coupling matrix A can be a random matrix. However, how to implement a random matrix on a quantum computer is still like not very clear. Yeah, so in the best scenario, if you can implement a random matrix, then it will be very good. Yeah.
I see. So is it easy to implement F? I mean, you demonstrate 3 level case and level case. Is it easy? I mean, to know the eigenvalue, or it doesn't matter. You just design the.
So you mean to choose this matrix A? Do I need to know the eigenvalues or
not A? I mean X.
So to choose this F, do I need to know the eigenvalue? No. So actually, yeah. So when we construct my function F, it only needs to satisfy this so this assumption where the head of F is a Fourier transform. So you can see that this condition 2, we don't need any requirement for the eigenvalues of capital H. You can just to construct some F satisfies this condition, then the algorithm will always succeed.
And how about A? You need to make sure it only jumps from high level to low level.
Oh yeah, so for the matrix A, to help our simulation, we hope that my matrix A can be a Hermitian matrix, and it's important that it's not block diagonal in the eigenbasis of H, but this is not a very restrictive constraint. So basically, what you can do is you can choose A to be a local operator such that like x1 c1 something like this. Yeah. So so it's always very easy for you to find the matrix A. Yeah. So in our numerical simulation, when we run the TFIM6 model, we directly choose A to be x1, and it the algorithm directly works, and we believe the choice of matrix A is very flexible.
I see. Okay. Okay. Thank you very much. Very nice.
Okay. Yeah. Thank you. Okay.
Okay. Do we have more questions?
Hi, I have some questions.
Yeah, sure.
Okay. In your slides, you say that your K can be expanded as the Fs and A. But how do we derive this expansion? This is we devise this formula in purpose, or we this is come from the property of the Lindblad dynamics?
Yeah, so this is a very good question. So actually, as I previously mentioned, so our Lindblad dynamics is inspired by the thermostat preparation. And in the regime of thermostat preparation, one very good dynamics, contains some operator called Davis operator. So the formula of the Davis operator is a little complicated, but if you look at the formula of the Davis operator, it's very similar to this formula. So the formula of Davis operator also has a integral, but it's a double integral. But here we further simplify it to the one variable integral. Essentially, this formula is inspired by the Davis operator for the thermostat preparation. Yeah.
Okay. And another question is, how do we know if I successfully prepare our ground state? How say that I stimulate time to t, and I can check I have successfully derived the ground state.
Yeah. So so this is also a very good question. So in fact, to the best of my knowledge, in general, you can't. Yeah. So So basically, what you can do is something like this. So yeah, I show you. So basically, what you can do is in the first graph. So basically, during your simulation, you can try to use the quantum phase estimation algorithm to measure its energy. Then what you hope is that you can see that the energy will keep decreasing. Then when you run the algorithm for enough long time, it stops decreasing. Then you expect that it's the ground state energy. But whether it is true, it's kind of unknown. What you can do is you might try to run the dynamics with another initial state and try to see whether it will converge to the same equilibrium energy. Yeah. So I think this is essentially the best you can do.
Okay, I see. And I have no questions. Thank you. Thank you very much.
Okay. Yeah. Good. Thank you.
Any more questions for the speaker? Okay, I think that's it. So let me thank you for accepting coming here and give us a very nice talk. And it's a very
yeah. So thank you for the invitation. Yeah. Okay.
Are you coming for QRT?
No. So I need to teach at that time, but I think my mental learning will go to QRT. Yeah.
Okay.
Okay. Yeah. Okay. Yeah. Thank you. Bye.